Taking a look at dissociation and major entities here today. So dissociation describes dissociating or breaking apart, particularly in water. So in this case, we're looking at the dissociation of NaCl in water, and you can see that NaCl is a crystal structure when it is a solid, okay, meaning the ions are packed together, unable to move. When they are placed in water, the polar nature of water allows the partial negative of oxygen to attract to the full negative ion of sodium, pulling it out of the crystal lattice. Same thing is happening for chlorine ions. Chlorine ions are negative though, and so the partial positive of water is pulling it out of the crystal. Anything that is a soluble ionic compound will start as a crystal lattice, and when put into water, the ions will separate and it dissolves. So dissociation is just describing that creation of positives and negatives in water. Arrhenius said that when a substance dissolves, particles of that substance separate from each other and disperse into the solution. And this determines whether the solution is an electrolyte, aka it conducts, or a non-electrolyte, it does not conduct. Understanding properties of solutions and the reactions that take place in the solutions helps us to know the major entities or what is present in any substance in its water environment. A dissociation is, again, the separation of ions that occurs when an ionic compound dissolves in water. We're going to take a look here at the dissociation equations and major entities for different substances. We'll look at ionic, molecular, and acidic substances. Ionic compounds can be divided into two different ideas. We can have a soluble ionic compound, or we can have an insoluble ionic compound. To decide this, after we know it's ionic, we need to look at the solubility table. Soluble ionic compounds will dissociate or split into their ions and can be shown using a dissociation equation. When we write a dissociation equation, we're going to write the ions that make our ionic compound separately. So aluminum sulfate as a solid ionic compound, when put into water, will make an aluminum ion. And it's now aqueous because it's dissolved in water. And a sulfate ion, which is also aqueous because it's dissolved in water. Note here that we have two aluminum ions. So when they split, there are actually two separate aluminum ions. And using the same rationale, there are three sulfates required, so we get three separate sulfate ions. This means that aluminum will split into 5 different pieces, 3 sulfates and 2 aluminum ions. The major entities are the idea that if we zoomed in on this solution, we're able to actually see the molecules, what would be present. Because we've tried to dissolve it in water, water will always be present as a major entity. It doesn't matter what type of compound you have. From there, because we know that aluminum sulfate breaks up into these ions, if I zoomed in, I would actually be able to see some aluminum ions floating around and sulfate ions floating around. I don't have to list the numbers, I'm not balancing here, okay? However, I have to list the different types of entities or things I would see in my beaker of water. If an ionic compound is insoluble, it means it does not dissociate in water. There will be no ions. All I'm going to see is the solid at the bottom not breaking apart. So it does not have a dissociation equation. So I will write its formula. I will draw an arrow and I will say no equation. And then when we list the major entities, there are no ions floating around in solution. However, at the bottom of the solution is the solid magnesium carbonate. It has not dissolved. There are no ions. Basic compounds follow under the ionic rules because basic compounds are ionic compounds that just have an OH minus in their formula. So I won't do this one, but what you'll need to do here is to check, is it soluble or insoluble, and write accordingly. Acidic compounds. Arrhenius says that all acids ionize, which is a fancy word for dissociate, in water to produce H ions and negative ions. We use the word ionize because technically acids look molecular, like HBr. These are both nonmetals, so it should be a molecular compound. So ionize just means dissociate, but for acids. All acids have an ionization equation. However, acids ionize to various different degrees. Strong acids have a very high degree of ionization. A strong acid breaks apart basically 100% in water. So that means that of all the HCl molecules I put into water, absolutely all of them basically will break up into their ions. This will be a little bit different for weak acids, so hang in there. All right, so again, that means that if I put in 100 molecules of HCl, all 100 would break up and I would get just H plus and just Cl minus lingering. There will be no more HCl's stuck together. So if we were to zoom in on our solution, there's water because we've tried to dissolve it in water, in this case successfully. And we will see H plus and Cl minus is hanging around in solution because it broke up entirely. I'm just listing again here. I am not making an equation, so I don't need to add any coefficients if there were any. There are 6 strong acids: perchloric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, sulfuric acid, and nitric acid. You must memorize these. I would highly recommend that you write out their formulas to remind yourself of what those formulas look like so that you can pick them out when you see them. If it's not a strong acid, it is a weak acid. These ones have a very low degree of ionization and are technically poor conductors. So the idea here is that, again, it's acidic. It breaks into its entities. In this case, we have acetic acid, which is not one of our 6 strong acids. So we're going to break it up into the 2 ions that made it, which was CH3COO minus acetate and H plus. What it means to be a weak acid is that it ionizes or breaks apart less than 50%. So of the 100 molecules I put in here, less than 50% of them will actually break up. So when I look at this in solution, the strong majority of them are still stuck together. Maybe one has broken apart in my little diagram here, but the major entity, what is there in the greatest quantity, again, is water. But this time it's the weak acid still stuck together because it is there in the greatest quantity. A weak acid, by definition, ionizes or breaks up less than 50%. Most of them are like about 1%. So of the 100 acid molecules I put into solution, only one of them is actually going to break apart. The other 99 will still be stuck together. So the ratio is a lot higher than what I've been able to draw here for you. Again, if it's not one of your 6 strong acids, it is a weak acid. Molecular compounds. To know what a molecular compound is going to do in water, you need to know if it's polar or non-polar. So go back to your bonding and decide, if that compound is polar or non-polar, or by memory, up to you. What you need to know, though, is that they do not dissociate in water, and they have no dissociation equation. That makes no sense, but based on the fact that I've just asked you to decide if they're polar or non-polar, but it does make a slight difference. So it doesn't matter whether they're polar or non-polar, they will have no equation. They don't make ions because they are not created from ions. They are sharing electrons to become a full octet. However, polar or non-polar changes the entities. Again, we start with water. In every case, we've tried to dissolve them. And if they are polar, they do dissolve in water. So glucose here, or sucrose, C12H22O11, is polar, and like dissolves like. Polar things dissolve in polar substances. So this will dissolve, and I will write it as C12H22O11, and instead of solid, it's now aqueous. It's dissolved, but it's still stuck together as an entire molecule. It has not broken up into separate ions. Non-polar molecules, however, do not dissolve in water. So when I put them into my beaker of water, what they will do is either float on the top, like our cyclohexane did, or if they're more dense, they will sink to the bottom, but they will not dissolve. They will make distinct layers. So C6H14, just C's and H's, is nonpolar. So C6H14 is going to remain in its original state of liquid. So whatever this nonpolar molecule is, keep the same state. So solid, liquid, or gas. This was a little table I thought might be helpful for you to remember how to classify or go about dissociation or major entities. Remember, we divided into 3 different categories. We had ionics, which included bases. We had molecular, and we have acidic compounds. Ionic compounds, to determine their dissociation in major entities, you needed to check their solubility. They were dependent on being soluble or insoluble. Molecular compounds, it depended whether they were polar or non-polar. And acids, it depended on whether they were strong, one of those 6, or a weak acid. And then here I just wrote a general equation for dissociation, and I wrote out the general idea for major entities in all cases, just to remind myself and summarize. Up to you if you'd like to use this, though. Your homework is the Understanding Solutions assignment. You can look at it online, but I also have a hard copy for everyone in class for you to complete.